Hi, I'm McKenna.
Hi, I'm Abby.
Today we are measuring an unknown mass by comparing it to gravity. And the first way that we did that was by using a hand balance. This is 200 grams and this is 50 grams. And this one I can just feel in my hand that it's heavier.
Another way that you can use hand balance is to use like inanimate objects or water bottles and see like which one is heavier, who has more water. So obviously I have more water than McKenna's water, so I can feel it in my hands on which one's heavier.
Okay, our next example is a teeter-totter, as we have right here. For this, the masses that we're trying to measure, my phone is the unknown mass. This is 200 grams. They must be the same distance from the center for the experiment to work. And right now it's balanced, so we know that my phone's mass is equal to 200 grams.
A teeter-totter is obviously way more accurate than doing a hand balance where you can just be like, oh, this feels heavier and this doesn't, because you're able to get like an even amount and see which like actually makes it work. So when using a spring to find unknown mass, we're going to be finding the mass of this clip. So when we clip it on, we see that it obviously it stretches. And using a ruler going to the centimeter side, when we measure it, it is about 16 and a half. So then we're going to take this clip off, and using our known masses, we're going to hook these on. So if we put one on and check, right here, we are at about 11 centimeters. So when we put our second one on, we are at 16 and a half, which means that when we total up these two, which this one is 20 grams, and this one is also 20 grams, so that is 40, that means this is also 40 grams, because when they stretch, they both were the 16 and a half centimeters.
Probably not.
Okay, so the most accurate of these three options is probably the spring extension, because you get exact measurements from the centimeters, and you're able to make exact comparisons. While on the teeter-totter, there's a lot of other factors, such as the distance from the center of the teeter-totter. Teeter-totter is probably the easiest, though, and the easiest for students to understand because they experience it in real life, on playgrounds, and balancing in general. So I feel like that would be the easiest one to use in the classroom for younger students.
So now we are going to be measuring the same object 10 different times. We're going to be doing that through springs. So here we have one spring that is already on the scale. We can see that that weighed 3 grams. So now we are going to map that using a histogram. So here we have our X for our number of springs. That was our first spring that weighed 3 grams, so we put an X there.
Okay, so our second spring that we just measured on our scale ended up being 3.19 grams. So that falls in the same category between 3 and 4 grams, so I'm going to add my X there.
Our next spring, we're going to put that on, and it is 2.98, so then, do you want to mark it?
Yeah.
So then we're going to go ahead and mark that. Perfect.
This is our fourth spring. Let's measure it. 2.99. So I'm going to mark it right here in between 2 and 3 grams.
So we're into our fifth spring now, so we're going to put that one on. And that one is 4.16, so that one does move our histogram over. So now we're going to put an X right by the 4.
Okay, so here's our completed histogram after we've added our springs. We can see that in between 3 and 4 grams was the most common weight for our springs, and we had a few outliers. We had one that was relatively pretty light, and then 2 that were actually between 6 and 7 grams.
So today we worked on measuring an unknown mass and then comparing it to gravity, and then again like figuring out which one had the most ease and accuracy, and then we kept remeasuring and found a histogram. And that was it for today.
We'll see you on Thursday.
Okay, so today we are measuring using triangles. So we're gonna measure the height of the door. So with that, like you kind of have to have something in here. So McKenna would sit here and like kind of like scratch down, and then I'm gonna go in its place because I'm 5 feet tall. And then I stood there until she told me like back up, back up. So then there she is, she's gonna scratch down. And when she tells me I'm good and I'm even with the door, then we're gonna go ahead and write down how far this is in between and what that measurement is, which this was 4 feet and this is 2 feet. So then we're gonna go ahead and draw that, which we'll show that in a second, and then we're gonna go ahead and do our math for that.
We're going to use similar triangles to find the height of the door. So I set up my equation like this. X is our unknown height. We were aware that this was 4 feet, Abby's 5 feet tall, and then this was 2 feet that was behind her, because from this angle these two objects looked like they were the same height. So we set it up in a ratio where it's 5 feet over 4 feet to find what this triangle was. And then we take the total 6 feet on the bottom of this fraction and set it up with our unknown number, the height of the door, which was x. We solved this ratio for 7.5.
Which ends up being the height of the door. Okay, so now we are working on measuring a different item 10 times to see the height of the door again. So we set up a histogram, which you can see here. And now instead of measuring me, we're gonna do McKenna, who's 5'5". So I'm now sitting, we've measured it, it's actually 7 feet back. So I'm sitting here and like you can see kind of from like my angle, McKenna is the same height as the door. So now we have our triangle set up here and we are gonna do our math now. So on our histogram, we've mapped now our first try, which was 7.5 here. And then we just did our second try with McKenna here. And you can see kind of how we set up our equation. So we did the 5.5 divided by that's supposed to be 5, sorry. 4.5, which is this, and then we have x over 7, which is our total length here, which got us 8.5. So we just did our second, or like our third trial, which we can see that we changed it. So now I'm only 6 feet away from McKenna. So obviously like that changed all of our distances here. So it was 5.5 divided by that 4.5 equals x over 6, and we got 7.3, which is mapped right there.
Okay, we just measured again, but this time Abby sitting 5.5 feet away from the wall. And from her angle, I need to be about 1.25 feet away from the door to look about the same height. And I'm 5'7", so 5.5 feet-ish. So we filled out this triangle. Sorry, there's so many. I was 1.25 away. Then I'm 5.5, so we set up 5.5 over 4.25, set it equal in our ratio to x over 1.25, solve for x, and got 7.1 feet. On my histogram, that added another x in between 7 and 7.5.
So here's our completed all of our triangles and our mapped histogram, which you can see. So the way that we did this was like moving ourselves to be closer, and then McKenna would have to adjust to be like in line with the door, and if I moved farther back, obviously she'd have to continue adjusting. So that's how we continue doing the rest of our 10 trials just like before, and mapping it out, we see that the average falls in between 7 and 7.5.
Okay, so now we're going to be using a tool called a caliper to measure something very, very, very small. As you can see, when we pull apart the caliper, it gives us a very exact measurement of a very small distance. We're actually going to be measuring this little piece of lead.
Okay, we just measured the lead, and it's about 0.7 millimeters, which is what it's supposed to be, so that's good. So now we're going to be showing like hand measurement. So if we look here, McKenna can measure from her thumb to middle finger, it's about 6, and she's going to go ahead and count that. Brooklyn is about 5, and I'm about 6.5 to my pointer finger.
So these are the hand measurements that we came up with. I got about 75 inches, Abby got 68.5, and Brooklyn got 60.
So we just actually measured the table, and they came out to be 71 inches.
So as you can see, using our hands was not accurate for measuring this table.
Okay, so now we're finding the area. So last time that I did it this way, which we knew I was about 6.5, so that whole thing ended up being 68.5. And then when I did it this way, I counted and I did this, and that gave me 5 times. That was 32.5, which gave us a total area of
2,226.25 inches squared.
Now to find the volume, so I took my hand again and I went down and I did my finger lengths, and I got about 4.5. So you can see McKenna here and Brooklyn did the math for that. So then go ahead. It ended up being, go ahead.
It ended up being 65,117.81 cubic inches.
If it were to be filled.
Okay, so we are looking to estimate the density of water. So we filled up this water and we calculated the volume of the cylinder that it fills up using pi r squared times height. We came up with 170.24 cubic centimeters. We put that in the bottom of our equation. We then weighed an empty container and subtracted that from this weight to get 140.19 grams. We plugged that into our equation and we got a density of about 0.823.
This was Science Lab for the week, so bye from
McKenna,
Abby, and Brooklyn.